This module provides an introduction to the concept of anti-collision in directional drilling operations. As drilling campaigns expand and fields mature, the number of wells within a given reservoir or platform location grows significantly. This creates a higher risk that new wellbores might approach too closely to or even intersect with existing wells. Anti-collision techniques are designed to mitigate this risk by continuously monitoring and comparing the trajectory of a subject well against the positions of nearby offset wells. The objective is to maintain safe clearances at all times, preventing equipment damage, production losses, or catastrophic events such as blowouts or cross-flow between reservoirs. This introduction will set the stage for understanding survey uncertainties, the tools and methods used to measure and manage positional error, and the scanning techniques applied during planning and execution. By mastering anti-collision principles, drilling teams gain confidence to work safely in crowded well environments, ensuring that each new well is drilled with precision while minimizing risks to existing infrastructure and personnel. This subject will be broken into 3 submodules. This is submodule 1 of 3. The objectives of this module are tailored to give you a comprehensive understanding of anti-collision practices and survey accuracy. At the end of this session, you should be able to explain the root causes of survey inaccuracies and outline the different tests used to detect and correct them. You will also become familiar with critical terminology, such as the ellipsoid of uncertainty, EOU, which describes the statistical boundary of positional error, and the travelling cylinder, which provides a visual representation of safe spacing around a well. In addition, you will learn how to plot wells and calculate distances between their paths. The module also reviews anti-collision plots, demonstrating how they are generated and interpreted to support safe drilling operations. Other essential topics include target sizing, which determines how accurately a well must be steered to intersect its reservoir target, and the structure of a surveying program, which sets the framework for systematic data collection and analysis. Measurement. While drilling, MWD tools play a crucial role in well trajectory monitoring, but despite their sophistication, they are subject to multiple sources of inaccuracy. These inaccuracies primarily affect direction and inclination readings. Factors contributing to these errors include the manufacturing tolerances of the sensors, misalignment between the sensor, circuit board, chassis, and collar, as well as issues with how the MWD collar aligns with the borehole itself. Cross-axial interference caused by magnetic material within the collar can also distort results. In addition, local magnetic anomalies or disturbances caused by solar activity introduce further complications. To maintain measurement reliability, periodic degaussing of the collar and recalibration of the direction and inclination package are necessary, usually performed every 3 months. Even with these precautions, inaccuracies can persist, so engineers must interpret MWD data with caution. Understanding the limitations of these measurements is critical to anti-collision planning, as underestimated errors in survey data could cause well paths to be plotted incorrectly, leading to unsafe assumptions about well spacing. MWD measurement inaccuracies can sometimes be difficult to detect during normal drilling operations, as faulty sensors may continue sending values that do not appear overtly wrong. This means operators may not immediately recognize errors. One common mitigation is resurveying selected points with a separate MWD tool to confirm readings and identify inconsistencies. Several corrective strategies are available. Reference survey station comparisons use the first survey point beyond the magnetic interference zone as a baseline. Long surveys involve transmitting each individual sensor reading to the surface for more detailed analysis. Roll tests are performed by changing the tool face orientation of the sensor, then repeating surveys to confirm alignment accuracy. Finally, 4 or 5 axis correction calculations are applied to compensate for systematic errors. These techniques improve the confidence in survey results and reduce the likelihood of plotting wells incorrectly. Without them, small errors could accumulate across multiple stations, leading to significant deviations from the intended trajectory. Anti-collision analysis is the structured process of scanning a subject well path against nearby offset wells to ensure safe clearances. This is done during planning, execution, and real-time monitoring. 3 key rules underpin effective anti-collision practice. First, software scans only from the points selected, typically each real or pseudo-survey station at 100-foot intervals. While acceptable for an overview, closer intervals must be applied where risks of close approach exist. Second, projection is critical. Like driving a car, one must look ahead 3 stands or more to anticipate hazards, rather than reacting only to immediate proximity. Finally, all planned slots or future wells should be included in scans to avoid inadvertently blocking access by drilling a current well too close to future trajectories. Following these rules ensures a proactive, forward-looking approach to anti-collision management, preventing surprises and maintaining operational flexibility for all planned wells. Center-to-center distance calculations form the geometric foundation of anti-collision scanning. There are 3 main methods to assess proximity between wells. The first is 3D least distance scanning, which acts like a radar, measuring the shortest possible separation from each selected analysis point to any surrounding offset well. The second is horizontal plane scanning, which evaluates well separations in the horizontal plane, but does not account for vertical differences. This method has limitations in complex 3-dimensional drilling environments. The third is normal plane scanning, which looks perpendicular to the well path, providing a more context-specific measurement of clearance. Each method has different applications, but understanding how and when to apply them is vital. 3D least distance is used for broad scanning, while normal plane scanning is especially important for traveling cylinder plots. By integrating these approaches, operators can maintain safe separation between wells throughout drilling operations. 3D least distance scanning is the primary method for anti-collision analysis. It calculates the minimum distance between the subject well and all offset wells at defined survey stations. This is done by projecting a line perpendicular to the trajectory of the offset to the subject well. This is a center-to-center distance. Think of it as a radar sweep that identifies the closest possible approach in all directions. This method is most effective for providing a general picture of spatial separation and is widely used in well planning software. However, while it is excellent for identifying risks, it must be complemented by projection and interpolation, particularly in areas of close proximity. An issue with this scan is that the closest distance may already be behind the subject, making it impossible to intersect. However, the 3D least distance method is the primary scan used in anti-collision, giving operators the awareness required to maintain safe drilling practices in increasingly crowded fields. It serves as the baseline tool for all subsequent anti-collision assessments. Horizontal plane scanning measures separation between wells by projecting analysis points in a flat horizontal plane. While this method can provide insight into relative well positions, it has significant limitations in 3-dimensional drilling. Because it only considers lateral displacement, vertical differences between wells may be overlooked. This makes horizontal plane scanning unreliable as a standalone method for anti-collision. For example, 2 wells may appear safely spaced in the horizontal view, but could in fact be dangerously close when vertical alignment is considered. Therefore, this method is not valid for robust anti-collision work. It can, however, serve as a supplementary visual tool to enhance understanding of relative well positions. This is represented in a spider plot, which is a horizontal view of the wells. Each well path on the plot should have TVD depth included to improve visualization. Operators must rely instead on more comprehensive scanning techniques such as 3D least distance or normal plane scanning to ensure true well separation and avoid unexpected proximity during drilling operations. Normal plane scanning evaluates well separation by projecting distances perpendicular to the well path. This method is essential for calculating travelling cylinder plots, which visually represent the uncertainty envelope around a well bore. A line perpendicular to the subject well is drawn to intersect with the offset well. The distance is the center-to-center distance. Unlike horizontal plane scanning, normal plane scanning captures the true risk of collision by accounting for the well trajectory and direction at each point. It provides the most accurate measure of clearance in complex drilling geometries. This approach ensures that offset wells are not only separated in distance but also in orientation relative to the subject well. By using normal plane scanning, operators can model clearances dynamically as the well progresses, integrating positional uncertainty into decision making. This makes it the only valid method for travelling cylinder analysis, ensuring both planned and real-time drilling maintain a safe margin from offset wells. This comparison summary consolidates the scanning methods and their applications. 3D least distance scanning is the primary tool for identifying minimum separation between wells and serves as the first line of anti-collision defense. Horizontal plane scanning, while useful for lateral visualization, is not considered valid for anti-collision due to its inability to account for vertical displacement. Normal plane scanning, on the other hand, is indispensable for travelling cylinder plots, providing the most accurate and trajectory-sensitive analysis of well spacing. By combining these methods appropriately, operators can create a layered approach to anti-collision, ensuring risks are identified from multiple perspectives. The summary emphasizes that while software tools automate much of this analysis, the understanding and judgment of drilling engineers remain critical. A well-informed operator can select the right method at the right time, safeguarding both current and future well operations in congested fields. So far, we have examined the various scanning methods and terminology related to the uncertainty of well locations. Let's move on to the ellipse of uncertainty, error models, and plot visualization tools. Please move on to complete the quiz. Thank you